Hello, welcome back. So, today we would learn the fracture and toughening mechanisms in brittle solids. So, every material behaves differently in a loading condition. If you take a tensile loading condition, so if you look at the brittle ceramic material, there is a linear response up to the point of the fracture. Whereas, in metals there is initially a linear response and then this is followed by a non-linear response. So, if you look at the stress and strain response for a polymeric material, a thermoplastic polymer material, there is a constant deformation at a low levels of stresses, which was preceded by a linear stress strain response. So, overall the stress strain response for the different classes of material is different. So, there is a difference in the linear response with respect to the slope of this stress and strain plot in a linear region. So, this slope is nothing but the elastic modulus, or we can call it as a stiffness parameter. So, the elastic modulus or the slope of the stress and strain in the elastic region is different from one material to another material. So, the elastic modulus is higher for the brittle material, followed by the ductile material and then a thermoplastic material. In addition to this elastic modulus difference, there is also difference in the total strain to failure, right. So, the failure occurs at a very less strain for the brittle material and a large strain for a ductile material, even larger strain for a thermoplastic polymeric material. So, there is difference in the elastic modulus, there is difference in the total strain to failure, and there is also difference in the load bearing capability. So, all these differences can be understood by the science behind this mechanical behavior. So, let us see the mechanical behavior of ceramic material. So, generally ceramic materials are studied for their strength measurement in a compressive loading conditions. Because ceramic materials are brittle, so the shaping of the specimen to a tensile test specimen like I shape, right. So, this itself, making this shape is itself difficult for the ceramic material. If you somehow make this shape of this material for the tensile testing, even while gripping itself they may break, right. So, generally these materials are studied for their strength property in a compressive loading conditions. So, compressive strength for a ceramic material is generally 8 times larger than the tensile strength. So, tensile strength, if at all you can measure the tensile strength, it is very less for a ceramic material. The higher compressive strength will be highly significant in a tribological applications, right. So, ceramics are mainly used for tribological applications because of the higher strength. So, all these tribological applications there is a compressive loading condition. So, you get a maximum benefit if you use a ceramic material. In addition to that, the elastic modulus is also the highest for the ceramic materials. If you look at this slope, this is highest for the ceramic materials. So, elastic modulus is highest, so it has also got great relevance towards Hertzian contact damage resistance. So, both these properties make the ceramic materials attractive for the tribological applications. Let us understand such a behavioral difference from a ductile material to a brittle material. So, in a ductile material, when an external stress is applied, there is a resultant shear stress and then because of the shear stress, these dislocations will be trying to move in a ductile material, whereas in a brittle material the crack will be propagating by breaking the bonds between these atoms in the adjoining planes. So, a propagation of crack will lead to a failure, generally it is a catastrophic failure, and so it is called a brittle failure, whereas this dislocation movement in a ductile material will lead to plastic deformation. So, you must note down these, the dislocation movement and the propagation of crack are present in both materials, but only the propagation of crack is dominant in a brittle material than the dislocation movement. So, you get a brittle fracture, that is a crack is propagating, they coalesce each other and then lead to fracture, so failure. Whereas in ductile material the dislocation movement is dominant than the propagation of a crack. So, you will have a effect, you will have a result as a plastic deformation, right. So, the domination of one phenomenon over the other actually is different from one material of one material to the other material. Let us understand it more clearly. Why there is a high toughness for the metallic materials, right. So, as I told, the crack propagation will also be there in a ductile material, but it is not significant. Let us understand how the propagation is not significant in a metallic material that leads to high toughness, right. So, if you have a crack is nothing but a defect, right. Every material has certain defects. So, you have one of the types of the defects is the crack, right. So, let us understand a metal which is a ductile material has certain concentration of cracks inside it. Now, you are applying a tensile stress over there, right. Externally you are applying certain stress sigma, right. So, this applied stress is the sigma applied. So, when the stress ahead of the crack tip, this region, when the stress ahead of the crack tip exceeds the metal's yield strength, you see every material has a certain yield strength. So, applied stress increases and then ahead of the crack tip it exceeds to a larger extent more than the yield strength of that certain material. Then what happens when the stress ahead of the crack tip exceeds the metal's yield strength, then the metal will yield locally. So, this region will be yielding locally. So, because of this there is a dissipation of energy, right. So, because of the dissipation of energy, so certain fraction of energy is consumed for this local yielding. So, there is a dissipation of energy, so that blends the crack tip. So, when it blends, the sharpness is reduced, so it will not be propagated easily, so that eventually leads to toughness. So, why metals are tough? So, why metals are tough? Because of the local yielding. This local yielding results in a higher toughness for a metallic material. But let us understand the mechanical behavior of a brittle material, right. So, we have seen there is a highest compressive strength amongst the three material categories of brittle material, ductile material and a thermoplastic polymeric material. Among these materials, the ceramics, a brittle material, has highest compressive strength and a highest elastic modulus, and it also possesses highest hardness because of the inherent bonding, because ceramics are materials in which the bonding is predominantly ionic or covalent, right. So, these bondings are stronger than the metallic bonding. So, because of that you get a superior properties of hardness, compressive strength, elastic modulus. So, it also gives a wear resistance, superior wear resistance. So, most of the tribological applications we require higher hardness, higher compressive strength, higher elastic modulus, that leads to superior wear resistance. So, but actually despite of having such a superior combination of the properties, these ceramics are less used in applications, or we can say the applications are often actually restricted because of the only problem with the brittleness, right. Brittleness can be understood as easy propagation of the cracks that leads to catastrophic failure can be understood as a brittleness. So, brittleness, so you can see the stress and strain plot for two materials which are brittle, one is aluminum oxide and glass, right. You can see the stress and strain plot for aluminum oxide and glass. So, both materials are brittle, that means there is a linear response, right, and then after this there is a fracture. Again there is a linear response and after this there is a fracture, only difference between them is the slope. So, elastic modulus is different. So, aluminum oxide has a higher elastic modulus than glass. Now, what is the common thing here? Just after the elastic deformation there is a fracture, right. So, the fracture is occurring because of the easy propagation of cracks. Now, let us understand this phenomenon more clearly. So, why there is no deformation in brittle materials, so ceramics, right. So, there is a, or I can say there is a negligible plastic deformation in ceramics. Now, the deformation which is a plastic deformation, the plastic deformation generally happens by slip mechanism, right. So, one of the dominant mechanisms for the deformation to occur is a slip. For the slip to occur, the atoms in one plane must slide past the atoms in the adjoining plane. Now, look at the ceramic materials. So, ceramic materials atoms are these are actually charged ions, right. So, the strong electrostatic repulsion prevents ions of the same charge from coming in close proximity to one another. So, it is very difficult for the ionic solid, right. If the ceramics are bonded by covalent bonding, so those covalent ceramics, the covalent bonding is a directional bonding which is much more stronger than the ionic bonding. So, strong bonding will not allow the slip to occur in covalent ceramics, right. So, if you have an ionic ceramics, this is arrangement of these ions in ionic solid, a ceramic. So, plus minus plus minus. So, the chance for having the slip is very less. Now, you can see only certain plane and a direction there is a chance for the slip to occur, whereas very less chance for the slip to occur. You can see whenever there is a positive and positive charge, or whenever there is a negative and negative charge, a slip will not occur, right. So, there must be some plane and a direction combination that we call a slip system. So, there must be some slip system where the slip is possible, right. That means the electrostatic repulsion can be minimum. So, very difficult to find such a slip system, or numbers of such slip systems in ionic solids are very less, right. In covalent solids, again I told you that covalent bonding is a directional bonding. So, this strong directional bonding will not allow the slip to occur. So, in both ionic or covalent bonded ceramic materials, the deformation by slip the deformation is negligible, or you can say absent, right. The negligible deformation is because of the difficulty for the slip, right. So, let us understand the brittleness in ceramic materials. What are the factors that actually give rise to such a brittleness? As we understood, ionic bonded ceramic materials, right. So, it is very difficult to find a slip system. The dislocation movement is restricted only to specific planes, mainly because of the charge neutrality conditions, right. If the ceramic material is a covalently bonded, highly covalent bonded material, in covalent bonding you require higher energy to discharge highly directional bonding, again it is difficult. And if at all there is a dislocation movement, right, the dislocation core width is much narrower than the metals. So, if you see the shear stress required to move a dislocation to give a Burgers vector magnitude deformation Such a shear stress is called peerless Nabarro shear stress, which is inversely proportional to the dislocation core width, right. So, the dislocation core width is narrower than the metal. So, the necessary peerless Nabarro shear stress is much higher. So, the possibility for the dislocation movement to give a deformation is less, right. And at the last, if you remember the von Mises criteria, which is one of the criteria which tells about the deformation possibility in a material. The deformation by default is a plastic deformation, right. So, the plastic deformation is possible only when there are more than 5 independent and active slip systems. In ceramics, it is difficult to find even 5 independent and active slip systems. So, because of this factor, the deformation is much less, right. So, if you combine all these factors, I can state that difficult for a ceramic grain to change its shape by rotation. So, you have a strain incompatibilities along the grain boundaries that lead to highly localized stresses. So, these localized stresses lead to brittle fracture, right. So, brittleness in ceramics are governed by these factors, right. Ionic bonding, covalent bonding, dislocation core width and less than 5 independent and active slip systems. So, these factors contribute for the brittleness in ceramic materials. Let us understand such a brittle behavior from the atomistic point of view, right. So, if you consider the bonding as like a spring like, right, as a spring like structure, right, spring like structure. So, you have certain in elastic response can be described as F equal to minus k into x, where this is F is the force, right, and k is the spring constant and x is the spring displacement, right. So, in an equilibrium position, there is the atoms are separated by an equilibrium distance. When they are subjected to external tensile stress, right. So, these atoms will be stretched, right. When the atoms are stretching, so you have a displacement more than the equilibrium displacement, right. So, because of this stretching, there is a rupture in the bonding that leads to fracture, right. So, along this plane there is a fracture. If you have the fracture is occurring because of this rupture that leads to cracks, right. The cracks will be having very high concentration at the crack tips. So, the crack propagates further and leads to fracture, right. Let us understand this crack influence on the brittleness, right. So, ceramics are processed generally by sintering. So, while sintering, so you have certain cracks already generated. Now, when an external stress is applied and the external stress is applied in a tensile manner, that means under tensile loading conditions. So, the largest crack with most favorable orientation would propagate in a direction perpendicular to the tensile axis, right. So, this crack will be propagating unstably and then they coalesce each other and then form a fracture plane and then the material will be failed. In case of compressive loading conditions, what happens? The cracks oriented closer to the axis of the compression are more likely to grow. So, that means cracks orient to as close to that of the compression axis before further growth. Now, you see the pre-existing crack and because of this orientation there forms a secondary cracks, right. So, there is a difficulty in the propagation of such crack, right. So, the difficulty in propagation of such a crack under compression loading condition also explains the exceptional compression strength that we saw around. Compressive strength is 8 times than the tensile strength for the ceramic materials. So, generally what happens in the tribological conditions, because of the compression loading, those cracks will be closed at the surface. So, there will not be propagation further, or I must say there is a difficulty in propagation of such crack in compression loading conditions. So, they are mostly appreciated in this tribology. So, ceramics are used because of their exceptional compressive strength. Let us understand the behavior of this crack by a fundamental theories, right, fundamental theory. So, there are actually two major theories that explains the brittleness of a material, right. So, a brittleness, or we can say the fracture of a solid material, can be understood by the concept of stress concentration at the crack tip. So, that was proposed by Inglis. So, it is called Inglis theory. Now, let us have a material, right, and then we have a crack at the edge, or there may be a crack inside the material, right. So, if you take a plate, right, that means the thickness is negligible. So, if you apply a tensile stress, so what happens, these crack will be expanding, right. So, and at the crack tip there is a large amount of stress concentration. The stress concentration at the crack tip edge can be described by the external applied stress and the crack size, if this is a crack edge C, or if the crack is inside the material 2C, right, this is 2C. Rho is the radius of curvature at the tip. So, for a condition having the C much larger than this rho, we can actually simplify the sigma maximum is 2 sigma into under root of C by rho, right. This sigma is the applied stress. So, stress concentration will be higher for the longer cracks and higher for the sharper cracks, right. So, if the crack is sharper, we will have stress concentration higher. If the crack length is large, then you have stress concentration. If the crack is sharp, you have higher concentration. If the length of the crack is more, then you have higher concentration. So, according to this Inglis theory, the fracture will take place when this stress concentration is equivalent to the theoretical cohesive strength, right. So, these theories are based on the mainly the rupture of these bonds and at the interatomic level. So, the interatomic bonds are broken and then it leads to the crack, and coalescence of this crack leads to fracture, right. But this was studied, this was found that every material has a strength less than the theoretical strength. Why? Because of the presence of defects. One of the defects is this crack, right. One of the defects is this crack. So, according to Inglis theory, the fracture will take place when sigma maximum equal to sigma theoretical. So, if you equate them, the theoretical strength to this maximum stress concentration, so you get this E is the elastic modulus, gamma is the surface energy, E0 is A naught is the interatomic distance, right. So, for a condition where the radius of the curvature at the of the crack tip equal to the interatomic distance, this is mostly possible, then you get a sigma equal to E gamma 4C power 1 by 2. So, this sigma is what we call fracture stress. So, you can actually understand the fracture stress is inversely proportional to square root of the crack length, right. So, in another theory which is based on the energy criterion, this was proposed by Griffith. So, it is called Griffith theory. So, for a ceramic plate with a central through thickness of crack length 2C. So, if you have a 2C crack, an elliptical which a major axis length is 2C, right, 2C. So, for a ceramic plate with central through thickness crack of length 2C under uniform tensile stress condition. So, the energy, the total system energy is a summation of elastic strain energy and then surface energy. This elastic strain energy is released for propagating a crack, and then the surface energy is required for creation of a new crack, right. So, you can see this delta u, yes, which is a positive, and delta u elastic strain energy is negative. So, we have a resultant of it, and if you for a spontaneous propagation of a crack, this must be 0, d delta u by dc equal to 0, then you will end up with the sigma c. So, d delta u by dc equal to 0. So, and if you can rearrange them, then you will get a sigma, that is the stress at which the fracture happens. We call that the critical stress, sigma c is the critical stress, is equal to under root of 2 gamma e by pi c star. C star is the critical crack length. That means, you have several cracks, the crack which is equivalent or more than the critical crack length, that will be contributing to the fracture, right. So, I can say in either way, fracture will occur if the applied stress is more than the critical stress here, right, or the crack length C is more than or equal to this critical crack length C star. The stress intensity factor K can be described as this, right, K equal to y into sigma into under root of pi c. So, y is a factor that depends on the location of the crack or orientation of the crack and even the loading condition. So, this K equal to y into sigma into under root of pi c, right. So, there are actually 3 modes of the crack opening. Mode 1 is like a tensile mode opening, this is tensile, right, and mode 2 sliding, mode 2 is the sliding mode, mode 3 is like a tearing. So, out of these crack opening modes, the tensile mode is considered to be the most dangerous, right. So, because when the crack is opening in a tensile direction, what happens, they can coalesce each other and then form a larger crack, the size of which can be more than the critical size. So, that will lead to fracture, right. So, the tensile mode is considered to be the most dangerous among the 3 modes, and most failures of brittle solids are largely due to the mode 1 failure. So, most of the studies are done in the tensile mode, crack opening mode, and then the stress intensity factor is called K1C. So, C is for the critical, this is one is mode 1 crack opening, K for the stress intensity factor. So, the critical stress intensity factor in mode 1 crack opening is equal to y into sigma c under root of pi c star. So, C star is the critical size, right, of the crack, and sigma c is the critical stress. Then this K1C can be described as a fracture toughness. We will see what is fracture toughness, how to measure it in another class, but the fracture toughness, the stress intensity factor is a parameter which is generally noted as a fracture toughness parameter. That is, fracture toughness can be defined as resistance against propagation of already existing crack. That means, crack has a certain length, right. So, in tribological application, the external force induced the K1 value should not exceed this critical value of the K1, that we call K1C of that material. So, every material has its own specific K1C, that means the K1C, which is fracture toughness, is the material parameter. So, we must also understand that the K1C value for a ceramic material is much lesser than the K1C value for a ductile metallic material. This unit for this K1C is MPa root meter, right. So, for a plain carbon steel, the K1C value is found to be around 100 MPa root meter, whereas the ceramic material, the K1C value is always less than 10 MPa root meter. That means, the K1C value, the fracture toughness is almost 1 order lesser than the fracture toughness of a ductile material. So, again the K1C is dependent on the size of this crack and as well as this critical stress, right. So, let us understand more with the cracking characteristics in a brittle material. So, cracking can be a conical cracking or a radial, median or lateral cracking. Let us understand this cracking in brittle materials. So, if you have a material which is indenting on the surface, or I must say the loading is a continuous distributive loading, right. This can be possible for with a spherical indenter or a spherical shaped body which is being loaded on the surface of this brittle material, right. So, what happens during this continuous loading with a blunt indenter? So, you can see the blunt indenter here. So, when it is touching and then you are applying load, you are increasing load, what happens? This material will crack at the edges, right. Crack initially forms at the indent edges and thereafter it propagates, but propagates at an angle downwards, right. So, as you are increasing the load, this crack will be propagating at an angle downwards. So, the entire crack pattern evolves to the conical geometry when you are unloading it, right. It increases, again it increases in length, and then when you are unloading, so it becomes more conical and then you will see this conical crack, right. There can be cracks, radial, median and lateral cracks in a brittle material. So, this can be possible with a sharp indenter, right. With a sharp indenter, so during initial loading the radial median cracks, you see this radial median cracks develop from the highly deformed zone just beneath the sharp indenter. So, when you are unloading it, when you are unloading taking above this indenter, the lateral crack pattern develops along the transverse direction. So, while unloading this crack will be propagating further, and with complete unloading the fully developed lateral cracks will intersect at the surface, free surface, and this material is removed, right. This material is removed. So, you can see after the indentation the surface you will have the impression of the indenter. Generally, if it is a Vickers indenter, you get a perfect square. At the edges of this square you will see all these cracks, right. So, this is very much significant in tribological conditions, right. For example, during abrasion process, harder solid which is sliding, right. So, that creates a multiple overlapping such lateral cracks. So, this lateral crack induced fracture is much more found in brittle materials, and such a fracture leads to the material removal called wear. So, this kind of cracking is more relevant in wear, right. So, if you look at this study of this indentation load versus the size of the crack, in either it is a radial crack or the conical crack, you see the severity of the mechanical wear damage with increase in the load, right. Severity of mechanical wear damage will increase with the increase in the load, right, increase in the load. So, there is a crack propagation that leads to failure that we call brittle fracture, right. So, if from the fundamental aspect, if the interaction between a growing crack and the microstructure can absorb certain amount of the energy available at the crack tip stress field, right, crack tip stress field, then the driving force for the crack propagation will be lowered. So, what happens? This becomes more blunted. When it becomes blunted, so you will have less chance for the propagation of such a crack. That means, in other words, the crack opening displacement will be consequently reduced. As a result, the crack tip will be blunted. Once the crack tip is blunted, it is very difficult to move, right. The propagation is restricted. So, you get a fracture toughness improvement. So, if you can find out a microstructure, or if you can generate a microstructure, if you can develop a microstructure, such a mechanism will be possible to improve the resistance against the crack growth, right. Such mechanisms to improve crack growth resistance are called toughening mechanisms. That means the brittle materials are made toughen by this microstructural engineering. So, the toughening mechanisms in brittle materials are mainly two types, right. One is the processing zone mechanism, another one is the bridging zone mechanism. So, let us see the processing zone mechanism. For example, micro crack, phase transformation or crack deflection are the major toughening mechanisms in processing zone. So, enhanced crack growth resistance in transformation toughened ceramics is realized due to phase transformation induced volume expansion or micro cracking or crack deflection in the process zone around the crack tip. So, in case of transformation toughening, for example, a transition from a tetragonal zirconia to monoclinic zirconia. So, this tetragonal to monoclinic zirconia in the crack tip stress field involves volume expansion. Generally, this volume expansion is around 4% to 5% volume expansion. So, because of the volume expansion, the material adjacent to or the adjacent to this crack tip will be monoclinic, right. There is a transformation. So, there is a material which is transformed to monoclinic, but in the vicinity of the crack tip, whereas the other material is still in the tetragonal zone. So, this is a tetragonal one, there is a monoclinic one, right. So, the tetragonal zirconia will be transformed to monoclinic zirconia under the applied stresses, right. So, the stress induced transformation will lead to monoclinic zirconia around the crack tip. So, what happens, and this leads to volume expansion. So, when the monoclinic zirconia is formed with a volume expansion, this material will be compressed at the crack tip, right. So, this material compresses the crack tip. So, the transformation compresses that crack tip. So, the crack will not be propagated easily. So, you get a toughening, right. So, in a constrained microstructure, this results in a compressive stresses on the crack faces that leads to closure of the crack tip. So, you get a toughening, right, or the stress induced will be used to create more micro cracks than these major cracks. So, what happens, the energy will be used in creating such a micro cracks. So, micro cracks, that means the lesser sized cracks, right, than the major crack here. So, material will be safe even if you have a micro cracks, because the size of the crack is less than the critical size of the crack for the brittle fracture. So, what is happening, the energy is consumed in creating such a micro crack. So, micro cracks will also compress this one, and as well as energy required to move this major crack will be reduced. So, you get a toughening. Certain materials you have crack deflection because of the second phases or any other reinforcement, right. So, you get a processing zone toughening mechanisms, micro cracking, phase transformation and crack deflection are the major toughening mechanisms in processing zone. In bridging zone mechanism, this type of toughening is generally realized in a composites. Composites reinforce, the materials reinforced with a fiber or a whisker, right. So, the whisker reinforced or fiber reinforced composites, you get a toughening mainly because of this bridging zone toughening mechanisms, namely fiber reinforcement or whisker reinforcement or ductile metal bridging. So, for example, silicon carbide matrix and silicon carbide fibers both are inherently brittle, but you get a toughness of by making this a composite of silicon carbide reinforced with a silicon carbide fiber because of the underlying mechanisms that involve crack bridging due to this fiber and crack interaction. So, you got this fiber, so the crack will be propagated either by breaking this fiber or by traveling along this the fiber length, right. So, in either case the energy required to propagate further will be reduced, right. So, you get a toughening. So, the toughness of these fiber reinforced ceramic composites can be very high, and the underlying mechanisms involve crack bridging due to this fiber crack interaction, right. Such interactions in composites essentially involves the matrix fiber debonding. So, either the bond debonding or matrix micro cracking in the crack wake of the matrix, the crack deflection at the interface, fiber pull out, and finally crack bridging. So, you get a toughening, right. So, you can see several examples schematically shown here. So, there is a transferred zone, it is a transferred zone here, you can see this zone is a transferred zone, this is a major crack. So, the aluminum oxide with an aluminum oxide particle reinforced aluminum or zirconium reinforced by zirconium diborate. So, in a composite material, the extent of fiber pull out as well as the properties of the matrix fiber interface strongly determines the toughness improvement, right. You can see this monolithic material, stress versus strain response for a monolithic material, and this is a fiber reinforced composite material. So, you can see the first the matrix is cracked, right. So, you can see there is a decrease in the stress, and then there is a ultimate tensile strength, right, it reaches, and fiber is pulled out. So, there is a serration. So, large numbers of serrations here. So, you can see the toughness actually is improved, the area under the curve is improved, which is a measure for the toughness with as compared to monolithic material, right, this is the area. So, you get a maximum improvement in the toughness if you use the fiber as a reinforcement in a composite. So, fiber toughening is also accompanied by the modulus enhancement. You can see this slope is increased here, and this is governed by the rule of mixture. The fiber reinforced composites, however, have their own limitation, which includes expensive production cycle, anisotropic properties with higher property along fiber direction, right. So, finally, there is one material called cermet, in which the ceramic grains are bonded by a metallic binder. So, in that material we call that material as cermet, because ceramic and a metallic both phases are present. So, in the crack tip stress field, the ductile flow of the metallic materials, metallic particles leading to bridging of the crack faces reduces the available driving force for the crack propagation. For example, tungsten carbide cobalt cermet material decreases with lowering of cobalt content. So, the amount of cobalt content is also an important factor in getting a proper improvement in the toughness. From the material development point of view, the critical amount of cobalt is required to facilitate the liquid phase sintering, and the balance of the hardness and toughness demands the tailoring of cobalt content, right. The toughness is improved either of these toughening mechanisms. So, these toughening mechanisms can be more than one, they may act simultaneously, but in certain cases we see the domination of one toughening mechanism than the other. So, we say certain mechanism is mainly responsible for the toughness. So, if you have a toughness improvement in combination with the hardness and elastic modulus improvement, you get a better wear resistance. So, in coming classes we will also see certain examples where the toughness can be improved by microstructural engineering, that means by incorporating such mechanisms of toughening. So, by toughening, by improving the toughness, we will see the resistance against the wear will also be improved, right. Thank you.